Hi, welcome to es301 Engineering Analysis. This is chapter 21 on Newton-Cotes integration. So here are the learning goals. At the end of this, you will recognize the 2D representation of an integration approximation. You will know the general Newton-Cotes integration formula. You'll be able to apply the following integration techniques: a linear or trapezoidal, Simpson's 1/3 rule, which is a quadratic, and Simpson's 3/8 rule, which is a tertiary. And you will know how to estimate the error in a numerical integration. So first, let's talk about numerical integration. And we'll talk about it in 2 dimensions, because that's the easiest way to think of it. But this can apply in as many dimensions as you want numerically. And what we want to do is we have some sort of function, and we'd like to numerically get an estimate of what the integral is. And in 2 dimensions, if you remember, the integral is the area underneath the curve. And so what I could do is I could go ahead and break this up into some little segments here, and then just go ahead and add the area underneath each one of these segments right there. And in order to determine what the area is underneath each segment, I might go ahead and just connect this with a straight line or a curved line or something like that. And we're going to look at those various formulas within this chapter. As I said, what we normally have when in a numerical integration is not the actual function itself, but a bunch of data points that we have, and this is what we want to integrate. And so we don't actually know how the curve fits through here. So this is where, as I said, we could go ahead and put maybe straight lines through them, and that would give us some sort of idea of what it is. Or what we could do is maybe take 3 points and go ahead and fit each one of these with a parabola, and that might be a little bit better representation. Or we could even do higher order polynomials. And so what we're going to do is we're going to look at the 3 different orders of polynomials that we might have, which would be a linear, a quadratic, or a tertiary. And what you can recognize is, first of all, it really depends on what data you have. Imagine if I didn't have this data point right there. If I didn't have that data point and I just connected these 2 lines, I'd have a fairly large amount of error. But even introducing a quadratic in it, so I would end up connecting these 3 points, I still would introduce quite an amount of error. So if you are actually missing data points when your function is changing a lot, there's really nothing that you can do in order to improve your estimate of what the integration formula is, no matter how high the power of the integration is. All right, so first I want to introduce just the general Newton-Cotes formula. Everything we're looking at will be an instance of this general formula. And so here what we're doing, and using the notation of the book, is that we have the integral, and the integral is represented as I, and we know from calculus, the integral between 2 limits, say a to b, is going to be the function dx. Now, normally we don't have this function, so we can't analytically integrate it. So what we're going to do is we're going to approximate it. That's what this symbol means here. It's approximately equal to the integral of some function that we are going to fit to it. And this is going to be a polynomial of some order. So it's called f of n, where n is the order of the polynomial. This function we can go ahead and integrate between the limits, and that will be an estimate of what our total integration is. So the function f of n, as I said, it's going to be a polynomial, and we can do it of any order that we want. And so if we did a constant, it obviously wouldn't be a very good estimate at all. If I did say a0 a1x, for example, that right there would be a linear polynomial, and so that would be more or less like a trapezoid rule, which we'll discuss when I'm connecting it with straight lines. Or I could go ahead and do a second order polynomial. So let's kind of look back at our data here. As I said, if I was to go ahead and just do a0 a1x, that would be connecting with straight lines, right? Because that's what that equation looks like, just a single version of x. Or if I went ahead and included the next order up, a2x squared, there what I would be doing is parabolas, and I would need 3 points in order to do the parabola points. And I could go ahead and go up to a third order, and that would be taking 4 points, and I'd be putting tertiary curves to each one of those. Let's go ahead and look at each one of these in order. So first, let's go ahead and look at the trapezoid rule. Call this linear, because what we're doing is our function f(n) of x is equal to a0 plus a1x, so it's just linear. And so if I look at my data points, what I'm doing is I'm taking 2 points and connecting them with a line, and then I want the area underneath it. And so the reason it's called trapezoid, if you don't, not obvious right there, just in the picture, is that should look like a trapezoid. So remember, normally in geometry we might draw a trapezoid this way, and then if we wanted to know the area of the trapezoid, often the formula will call those little areas big B and little b, this over here being the height, and so the area would equal 1/2 big B plus little b times the height. So there's a little 1/2 in there. And that would be the area of what that trapezoid is. Now, if I was just to turn this trapezoid on its side and make one side flat, so it would do this way, and then turn it on its side, turn it in that direction right there, then I would come up and have the trapezoid that I've shown here. And so effectively this taller half would be big B, this would be over little b, and then this area right over here would be h, which is the height of it. And so now I can go ahead and determine what the areas of each one of these little segments are. And so this is what the integration of just between these 2 points would be. So b minus a, normally they're going to call this point b and this one over here a. Sorry about the mixing of notation where first I called b the height. This right over here would be f at b, and this right over here would be f at a, right? That's the height of these. And then right over here I have b minus a, that's going to be what h is, and then there's my 1/2 time. I'm just going to add up each one of those, and I'm going to do that for each one of the little linear segments that I have. So if I have n points, I'm going to have n minus 1 segments that I need to go ahead and sum to give myself my numerical integration estimate of what I is. Now let's look at the next order up, which would be Simpson's 1/3 rule. And so Simpson's 1/3 rule says what I'm going to do is I'm going to fit a second order polynomial. So I'm going to fit something like a0 plus a1x plus a2x squared. And so actually I'm going to do a little different form from this. What I'm going to go ahead and use instead is going to be a Lagrange polynomial. So if you remember Lagrange polynomials from chapter 18, and so it's just a little different form than this right over here, but it ends up with the same idea. And what I'm going to do is I'm going to fix 3 points on my quadratic curve to where my function is, and then I'm going to stick my quadratic right in there. And so if I was to go ahead and do this, there's a little bit of calculus and some algebraic manipulation, but you end up with a fairly simple formula, where here I've got an estimate of what the integral is. Integral of I, and it's h over 1/3, so there's where the idea of the name 1/3 rule comes from, h over 1/3, and then I'm evaluating my function for 3 points. So back at my picture, this right over here is considered x2, that's x1, and this is x0. So I evaluate my function. I'm taking the value of the function there, 4 times the value there, and then I'm going to add the value there, and then I'm going to go ahead and divide it by 3. And the whole thing is multiplied by h. H is the distance between 2 data points. We're assuming at this point all of our data points are equally spaced, and so that is h. Another formulation you'll see is a little bit different over here, where we have b minus a, and then we have 6 in the denominator. And again, that is that this idea x2 is equal to b, and x0 is equal to a. So that's the distance between 2 different data points, and either one of those functions work. Now note that what I'm doing now is I'm fitting a single parabola to every 3 points, and so that if I had another 2 points, I could fit another parabola there. You might wonder, what happens if you have one final straggling point at the end, since you don't have a 3-order polynomial to do? Well, you could just do a trapezoid rule at the end, or the other option is to go ahead and then fit a parabola through the last 3 points, but we don't want to double count this area, so we'll just go ahead and evaluate our integral from there. And effectively what we'll be doing, if you look at, there's kind of some of the nitty-gritty of the integral that I have. Let me erase some of that just to kind of clean this up. So this is the integration of my Lagrange polynomial. And so normally this integration would go from x0 to x2, and you would evaluate that integral. Well, you could still do the same integral, but just evaluate it from x1 to x2, and those would be my last 2 points. And that would give you what? This whole quadratic that fits 3 points, but we're only looking at the area between the last 2. So those are other 2 different alternative ways you can do it. It depends on how accurate you need to be for that last little segment. All right, the last one I want to look at is Simpson's 3/8 rule, and you can probably get a pretty good idea what's going to happen here. Now what I'm going to do is I'm going to take 4 points, and I'm going to fit a tertiary polynomial to it. So this is going to be a0 plus a1x plus a2x squared plus a3x cubed. And right, we recognize that we need 4 points because we have these 4 constants, a0 through a3. And with that, I can fit my 3rd order Lagrange polynomial through those 3 points. Formula looks somewhat similar, okay, but now I have this coefficient of 3/8, so hence the name Simpson's 3/8 rule. Again, h is the distance just between 2 points, and so often you'll have this alternative formulation where this last one, which is now x3, is considered b, and the first one over here is considered a, which is x0. You can go ahead and use either one. When you're numerically implementing it, depends on which is an easier number for you to go ahead and carry through. So the last thing I want to mention is how do we estimate integration error? And here the best we can do is just get some sort of ballpark idea what the integration error is. And the reason is we generally don't know what the function is. We'll look in the next chapter a little bit of when you know the function. But normally you just have data points and you have no idea what the function is that goes between them. And so what we know, and there's some derivation in the book for this amount of error. It's a bound on the error. You don't need to worry too much about how you arrive at it. But let me just explain it. So this is the error, and it's sub t, meaning it's the true error. And the true error is going to be this minus 1/12. Here I have a second order derivative of the function that occurs somewhere between b and a. And then I've got this quantity ba to the cubed. Now this, I think this is Greek letters chi. Where does that occur? That occurs somewhere in this region between b and a. But you don't know where it is. And so like I said, this kind of gives you an idea. So it's only an estimate because you wouldn't know where to evaluate it. At some point, if you evaluate the second order derivative at exactly that point, you'll get the true error. But you don't know where that is. And so often what we'll do is we'll try to approximate the true error with a little bit of approximation. And what we'll do now is instead of since we don't know exactly where chi occurs, we'll go ahead and just take maybe the average second order derivative throughout this whole region right in there and say that, well, that's probably an approximate estimate of what the second order derivative would have been at that point. So EA will never be exactly equal to ET, but they should be on somewhat the same order of magnitude. Right, so let's just look kind of how you might implement that. And so let's kind of just look at this point right over here, these 3 points, and imagine that I had fit a parabola between them right there, and I wanted to get some idea of what the approximate error was. Well, I need to get the second order derivative, and what I'm going to do to get that second order derivative, I can do kind of a simple estimate of the numeric derivative. We'll look at this more in detail in a couple chapters, but we've seen this before where we can say f double prime is approximately equal to f at x2 minus 2f at x1 minus f at x0 all of that over x2 minus x naught squared. Or you could think of this as b minus a, either way you want. So this right over here is x2, this over here is x naught, right? And all this is just doing a finite difference twice to give myself an approximate value of what the second order derivative is using these 3 points. And that way you can get an idea of what the error is. Again, it's always sort of an estimate, just a ballpark number. But at least it gives you an idea of what your error would be. Okay, let's go ahead and review what we looked at in this video. We saw that Newton-Cotes is a general scheme for numerically approximating a function. What we're doing is we're approximating it as a polynomial, and then we're integrating that polynomial. There's 3 common techniques. There's the trapezoid rule, Simpson's 1/3 rule, and Simpson's 3/8 rule. The most common actually is Simpson's 1/3 rule, or sometimes trapezoid is fine if your data points are fairly close together. We saw that Simpson's rule involves fitting Lagrange polynomials, either 3 points for the 1/3 rule or 4 points for the 3/8 rule. And then last thing we looked at was that the error can usually only be approximated, and it requires an approximation of the second order derivative. So it gives you an order of magnitude of what the error is, and that's about the best that we can do.